Hello and welcome to this webinar. My name is Ali Yahya. I'm the VP for IonFlux product. Today I would like to talk about how we improved flow control accuracy and precision for better ligand-gated assays. I will talk about the fluidic system and show you some preliminary results from acetylcholine and GABA receptors. IonFlux systems are well known for best-in-class ligand-gated assays. Here we demonstrate how IonFlux Mercury, our new addition to the IonFlux family, enhances on its predecessor even more. To ask questions, please use the entry box on the side of the webinar. I will read them at the end and answer them the best I can. If you have very detailed questions, you can always reach me later and have a discussion. In addition, I invite you to visit our website and view all the other webinars we have on IonFlux systems, presented by our team and by different customers. We also have application notes, posters, and publication information that cover the use of IonFlux in different assays. And if you have not done it already, please subscribe to our mailing list. A bit of background about Fluxion Biosciences. The company was founded in 2005. Our headquarters are now in Alameda, California, right across the bay from where we used to be in South San Francisco. We have three main product lines, all based on microfluidics technology and catering to different disciplines. Each platform has its own website. Liquid biopsy with IonFlux Systems, Citation Manager, and Spotlight 59. Cellular analysis with BioFlux 200 and BioFlux 1000Z systems. These systems are used for live cell imaging under flow, and they cater to microbiology, immunology, oncology, and hematology. And of course, IonFlux with the two new updated systems, IonFlux Mercury and IonFlux Mercury HD. IonFlux Mercury is the most integrated automated patch clamp system on the market today. The box that you see rotating integrates the fluidic system, the amplifiers, the operating computer, and a touchscreen. It has the footprint of a plate reader, so it can fit easily on a benchtop. In fact, you can put the system on a trolley and move it around. All you need is power, vacuum, and pressure input. What makes it very compact and integrated is its unique ability to do in-plate movement of solutions. This means that there is no need for an attached liquid handler to move solutions. The lack of a liquid handler and the dependence on pneumatics gives IonFlux a lower price range from the competition, but also capabilities that are quite unique, specifically with ligand-gated studies. IonFlux Mercury is based on the original two flavors of IonFlux and comes as 16 with 16 amplifiers or HD with 64 amplifier models. Both systems share exactly the same technology with regard to fluidics and are only different by the number of channels they record from. Both systems can come with and without temperature control and with and without current clamp. Here are the specs for IonFlux Mercury with 16 channels and IonFlux Mercury HD with 64 channels. You can see that the system retains similar dimensions to the previous generation IonFlux 16 and HD while having the computer and touchscreen fully integrated. Effectively, Mercury is smaller than the original systems due to a major overhaul of the fluidic system in the body. This overhaul gives it a much precise and predictable control over fluidics, and I will explain that later. The amplifiers and software have been updated too, allowing for longer sweeps recordings. We measured 300-second sweeps with continuous recordings at 500 Hz, so pretty long. Temperature control can be achieved via an integrated heater right under the plate, allowing for a precise and fast heating from ambient to 40 degrees, all controlled via software and programmed at different stages of the assay. Cooling can be achieved using an external cooler heater. Amplifiers can record in voltage clamp and current clamp and can switch back and forth within the same assay. Operating system is now Windows 10 64-bit. So to understand how the new Mercury upgraded fluidics can enhance ligand and also voltage-gated assays, it is important to take a quick look on the mechanism of IonFlux action. The system uses SPS plate format, 96 well for 16 and 384 well for HD. Although the plates are standard and can be filled by any liquid handler or automated pipetting system in your lab, their bottoms are not solid. They have been integrated with an intricate array of microfluidics where cells and solutions travel under pneumatic control. Okay, here is a 384 well plate with the microfluidics showing. Each plate is divided into zones, 4 for HT and 2 for 16. Within each zone, we have experimental patterns. We have 4 experimental patterns per zone for a 16 and 8 per zone for HT. If we look closely at one of these experimental patterns, and we then flip it and superimpose the schematic, we basically have 2 traps. This is where we have intracellular solutions and where the cells are trapped. Each trap has its own independent amplifier channel. So in each experiment, we have 2 independent recordings for the same experiment. Hence, if you do the calculations, for an HT we have 4 zones, each with 8 experimental patterns, as I said, with each patterns having 2 recordings, hence 64 channels per plate. In each experimental pattern we have 8 compound wells that can contain whatever you like, different compounds, agonist, antagonist, whatever is needed for the experiment. The in well is where you add your cells and the out is the waste, all independent across the plate. Hence, within a single plate we can test about approximately 256 different compounds or concentrations, as well as 64 different intracellular solutions at the same time. Just to note that due to the independent microfluidics, each compound has its own conduit. Hence, there is no mixing between compounds due to shared pipetting system or stacking, no cross-contamination either, no pipetting delays due to independence, no pipetting delays due to dependence on a liquid handler, and considering that the recording electrodes are in the traps and the ground is upstream from the compound, there is no electrode-compound contact, and hence the machine stays perfectly clean between experiments. As for recording from cells, all IonFlux machines can record an ensemble with 20 cells per recording, achieving a high success rate. It is important to note that currents are summed, not artificially averaged. So in ensemble, you are recording from 20 cells all together, and hence your currents tend to be quite large. Also, you can do single cells recording by simply choosing single cell plates. In both ensemble and single cells, the machine achieves gigaseal recordings. Gigaseals appear as gigaohm resistance when in single cells, but appear as megaohm resistances in ensemble, even though the machine is achieving gigaseals. I can explain this offline if you like at some point, if anybody wants to understand it a bit more. Suffice to say that if you record 50 megaohm resistance in ensemble, you have mostly gigaseal recordings across the 20 cells. The system is quite simple to operate. You fill your compound wells, your traps, and you add your cells into the in well. Once the plate goes in, the machine will prime all the wells. The cells flow in and are trapped. This video shows that the cells are trapped while flowing, but this is not completely correct. In fact, the machine interrupts the flow in order to trap the cells better. Once the cells are trapped and sealed, extra suction will break the seal to form whole cell patch clamp. This video is quite nice. It shows the process of trapping the cells. The plates are transparent and access to them is feasible, so not only you can record the cells being patched, but you can shine light on them for photosensitive channel studies. Here you can see that the cells are flying by, then the flow is interrupted. They are trapped, then the flow starts again. You get new cells and trapped again until all the holes are covered. Then after all the holes are covered, you'll see that all of the other cells are afterwards flying by because of the continuous flow. Here we go, they're all flying by. So once the cells are ready and the main channel is flowing, a simple valve opening allows compounds to flow to the cells. The compounds are at the same side as the cells, so when compounds are flowing, the cells will only see the compound. In addition, a wash step is a simple gap between the compounds. So if you have each compound flowing one after the other, there will be no wash step. However, if you have it separated by time, as you see in this cartoon, then you will have wash steps. It is as simple as that. So in effect, the cells are continuously washed either by compound or by any other solution since the flow is continuously flowing. So in essence, IonFlux system provide very efficient solution delivery compared to liquid handlers in other systems. In fact, what you see here is happening in all experimental patterns all at the same time. So it is a very fast process, specifically for ligand-gated assays. Okay, so I will dive deeper into this and attempt to explain how the updated fluidic control is enhanced in Mercury. So bear with me on this. If we look deeper into what's happening in the main channel, let's assume this is where the cells are, and this is a compound well. Main flow in the main channel is going forward towards the cell. At the same time, the main flow is exerting pressure on the compound wells. With time, if we don't do anything, the pressure in the main channel is going to push the compound backwards, and this will cause a diffusion layer between the compound and the main solution. This diffusion layer will be seen by the cells when the compound comes out from its well. So, not very good. In order to decrease the diffusion, we need to exert an opposite push from the compound side. We call this backflow pressure. This pressure system is active all the time when the compound valves are closed. But here is the problem. If the pressure is equal to the main channel pressure, to minimize diffusion, slight error in the regulators and variability in the system may cause the compounds to come out and possibly streak down to the cells. Also not good. So with IonFlux, the two pressures, main channel and backflow, are kept in sync, and backflow pressure being 80% of the pressure of the main channel. This is great. We can minimize diffusion to the lowest possible using the equipment we have. This is the case for all IonFlux systems to date. It's a great system, but still has a diffusion layer, which, with time, can increase as the main channel keeps on exerting pressure and push on the compounds. Okay, so how can we make it better? With IonFlux, the pneumatic system can only do 80% difference to be safe. With Mercury, we went back to the main design and restructured the fluidic system completely in the machine. Together with our vastly superior regulators and a lot of magic in pneumatic design, specifically from the engineers, we were able to achieve 98% backflow pressure while keeping it completely stable and no streaking of the compound. Hence, with the new fluidic system in IonFlux Mercury, we can achieve the lowest possible diffusion between compound and main channel. In addition, even though the main channel is still pushing on the compound, it will take hours before any real diffusion is seen, which is way beyond the scope of the experiment. The results can be seen easily in a conductivity experiment that we devised. If we simply add saline solution in the traps and the main channel, if we simply add saline solutions in the traps, If we simply add saline solutions in the traps and the main channel and establish a step in voltage clamp, we would see a continuous current, just like what you see here. However, just like what you see in this part. However, if we add pure water into the compound wells and open the wells, when the water flow, the resistance would go way up and hence the current would go down to zero, just like you see here. When the compound is turned off, the current will come back. If we put a cursor to record the current before the flow and another one after the flow, a simple subtraction would tell us if water is flowing or not. So here's one cursor and here's the other cursor, and if we subtract them from each other, we should get a point that tells us that there was a change when water came in. And as you can see here, we actually added water into all of the compounds and we flew one after the other. We kind of flow them one after the other, and you can see that there was a point going down every time that water was coming in. So which means that every single compound well had water in it. Okay, however, if we take all of these compound recordings or water recordings and we put them on top of each other, superimpose them, we can see that they are not exactly the same. This means that the main channel was pushing all the time on the compound well, in this case water, and with compound 8 the diffusion layer was larger, so it took longer for pure water to come out. In case you were wondering, this is compound 1. You can see it's the fastest one opening, and then compound 8 is actually here, which is the last one opening. So as time went by, as there was more push and therefore there was a more delay in order for water to come out. On the other hand, this did not happen with mercury. This is compound 1 and this is compound 8. You can see that they are very close to each other. Of course, mercury is set to 98, so there's still a 2% difference, but still the difference is minimal compared to what you were seeing with the regular IonFlux. Even comparing the same compound wells between systems, so if we take compound 1 from IonFlux and compound 1 from mercury and we superimpose them, we just superimpose the opening, we can see that with IonFlux it's this way, with mercury it's that way. So it is definitely faster. Okay, so how does all this affect cell assays? We obviously looked at cells that are very much affected with the slightest diffusion between the agonist and the bathing solution. Nicotinic acetylcholine receptors are great candidates for these tests. We use Te671 cells. These are human rhabdomyosarcoma cells, I hope I pronounced it right, which are widely used. They have a native acetylcholine receptor as well as a sodium channel, making them ideal candidates. Of course, we use the acetylcholine receptor for these tests. Now, just to recap, acetylcholine receptors are known for being affected by the slightest concentration of acetylcholine in solution. With the presence of the agonist, they activate and then they deactivate. As long as the agonist is there, they are desensitized. So you need to wash acetylcholine completely before you can activate them again. This used to be a problem with a lot of APC's system because they cannot really wash properly. However, with IonFlux, it's not that much of a problem because IonFlux, of course, washes really well. So to summarize, they can desensitize before they activate if the addition of the agonist was gradual and not abrupt, and they are also affected by diffusion, and they are also affected by not washing acetylcholine properly, so they need continuous flow. So this slide is taken from a paper by Reitstatter et al. In 1998 showing single-cell recordings of the acetylcholine receptor in Te671 cells. The pulses were 1 second in length with 1 millimolar ACH. So a desensitizing pulse, which is term D, is followed by subsequent pulses after 10 seconds of wash, 40, 80, 120, and 200. And you can see that it is affected by the length of wash and is also affected by the presence of acetylcholine in the solution. So you can see how it's activating and deactivating straight away, and it's staying desensitized until acetylcholine is washed away. Now these traces are from IonFlux. They are from ensemble recordings. Again, Te671 cells were subjected to 1 millimolar ACH. First addition after 30 seconds of wash period from the desensitizing step, and the second after 97 seconds. So this is after 30 seconds, and this is after 97 seconds. Notice that there is a delay in the application, but still the currents are quite nice. Quite consistent, showing the ability of IonFlux systems to wash away acetylcholine. To the right, however, you can see another recording from mercury, this time with the same time period and at the same scale. Notice that the delay is nearly gone. The currents are different. The currents at different times are basically superimposable. You can see that the delay here is much shorter compared to here. Now, how is this affecting us? In most cases, we find that the currents do recover very fast with mercury. In this slide, we looked at how effective is the recovery of the current. We simply normalized all of the peak currents to the current with the longest wash phase. These are sequential pulses that are getting further and further apart. Hence, the one to the right is the one after the longest wash period. The plot shows average of 27 recordings with standard deviation. You can see that from well to well, there is variability at the start, and it's largest between the recordings. So at the start, there's actually very large variability, as you can see here. So some cells needed time to recover while others were already recovered. Sorry about that. Here we go. Now this, of course, we saw it being decreased markedly with mercury. Here we have 24 wells with same condition. Notice that the curve is now flatter with minimal variability. So not only was there less variability, but also less rundown of the current. This is before, and you can see here how it actually curved You can see also that this is actually larger than this guy, and it's when you go to Mercury, you can see that the variation now is much less and it's much flatter. Now, the following data was recorded with Alpha 7, and this data was recorded at Eurofins. They tested a Mercury prototype and have seen some very nice results. For Alpha 7 tests, the cells used were I don't know if you call them precise ion, precision cylinder 3, or CYL3097, expressing nicotinic acetylcholine alpha 7 receptors. Information about these cells can be found at Eurofin's website, including all of the services that they provide with them. And I would like to thank Dr. Hae-Yang David Wei for providing the data. Just like before, alpha 7 cells were patched in ensemble format and were subjected to repeating addition of acetylcholine. You can see how the current slowly recovered from desensitization, but then as time went by and the wash period became longer, it decreased, showing either rundown or desensitization. Notice that? Now, now to the right, you see sweeps from 6 seconds and 10 seconds. So it's the first one and the last one, and they're superimposed. And you can see that there's a marked delay. Now with Mercury, on the other hand, when superimposed, you can see that the 6 and the 510 are nearly identical. This means that once the current recovers, it does recover. You can see here that basically this and this are basically the same. Also, you can notice that the current is much more stable as time went by. Now, obviously here I'm showing you a single well, but did we see this in all of the other wells or all of the other experiments? So what we did is that we took multiple experiments and we took the points here. So here we have peak currents after 6 seconds and after 5-10 seconds, right dots. So the left dots after 6 seconds and the right dots after 5-10 seconds from different wells. Notice that it shows that in most cases that the current became larger after the longer wash period. 1 or 2 are going up and the plot, but most are going down. Now, of course, we did not see the same thing with Mercury. With Mercury, what we saw is that the current stayed mostly the same. Again, some are going up and some are going down, but most staying the same. While none of the currents on the left stayed the same. So we have a higher consistency and faster recovery with Mercury. So it did recover faster, and it basically stayed the same. It did not go up, did not go down. Now there are some which actually did decrease, but most of them stayed in the same way. Now, the following data is also from Eurofins, and it's actually with GABA A, and it's a cylinder or CYL3053. Now with GABA, we saw that Mercury increases the stability and reproducibility of the current response from cell to cell. So the panel shows responses to successive additions of GABA initiated sorry. So the panel shows response to successive additions of GABA initiating receptor currents. So if we measure the peak versus time, we can see that the GABA currents were elicited and mostly stabilized after successive additions. So as we kept on adding GABA, one after the other, you can see that we get responses one after the other, and it's mostly stable in most wells, as you can see here. Now, if we superimpose, for example, we take these guys here and we superimpose them from different wells, we can see that there is variability for the response for each well from cell to cell. However, when we did the same thing with Mercury, with the same cells, same experiments, same conditions, one after the other, so we did this, and then afterwards we did this on Mercury, you can see actually that, it's not done with us, it was done at Eurofins. They did it all at the same day and the same time. You can see here that it was way more stable. Most of the currents were actually completely flat after this initial step here. And if you superimpose the currents, you can see that they are superimposable, even coming from different wells. They're all starting nearly at the same time. So, to summarize, IonFlux Mercury is a highly integrated and easy to operate APC with continuous flow, temperature control, and current clamp, and the new Mercury fluidic system provides a clear enhancement to the well-established IonFlux fluidic system, allowing for better ligand-gated current stability and reproducibility. And I would like to answer some of your questions. Okay. Can old IonFlux systems be upgraded? Yes, they can. We are presently expanding on these options, and they're all going to be provided on the website later on. Um, we are not sure about the 16 if it can be upgraded because of changes in the way that it actually works, but the HT definitely can be upgraded, and we do have different pricing options for the different upgrades. You can either upgrade the fluidics of the system, or you can upgrade the whole system, including adding current clamp and everything else. Are the new systems more expensive than the old ones? I cannot really talk about pricing right now, but I would not say that they're more expensive. I would say that they're just as competitive as the previous systems, since um, it's based on the same technology with more enhancements, uh, better way of doing things, but it is still the same price points and the same competitiveness. Are the plates the same? What about the assays? Can they migrate? Yes, the plates are the same. We still have exactly the same plates as before, the single cell plates and the ensemble plates. We did not change that. With regard to the assays, yes, all of the assays and all of the validation that has been done before is completely transferable to the new system. The software is not exactly the same, but the software will definitely import all of your previous assays and will definitely adapt them to the new system. With slight modification only just to adjust for the better fluidics. But other than that, it can run straight away. So you can take your assay, for example, from before and apply it, and it will run exactly as IonFlux, but you can also optimize it a little bit in order to get the better flexibility from the new fluidics. Okay, if, let me see. Okay, if there's no more questions, then I will stop right now. In fact, actually, if you do have any more questions, you can always contact me directly and we can discuss all of your questions and discuss them offline. Thank you very much for attending the webinar, and please don't forget to subscribe to our mailing list so that you can receive notifications for more webinars coming up later on in the future. Thank you very much.